And the geometry of this simple problem is a square box. It's in two-dimensional flow only. It's a box which is L by L. That'll be non-dimensionalized to 1 by 1. So it's a square box. And the boundary conditions are on the bottom, no slip. On the side walls, no slip. So there's nothing happening on the sides and the bottom. And the flow only exists because you drive the top plate at a velocity. So the top plate, which is y equals L, from x goes from 0 to L, will be driven at some velocity, and we have to discuss what that will be. Many people take it to be a constant, and they're rather foolish to take a constant, as we shall see. And then we need an answer. We need to get an answer. So the question is, can you please find the force on the top? If I'm going to drag the top plate sideways, what force do I have to apply? So it's a single number. So if you look at a single number, you can ask, is it three-figure accuracy accurate? So before you start writing any code, you might understand what the problem is. It's nice if you understand what the answer is going to be up to a factor of 2. So what's going on in this calculation? You should understand the physics of that. In fact, the other way around is quite good, that when you arrive at in a new problem, you've modeled the problem, and you've got some equations you'd like to solve, it's very good to test, do you understand these equations, by how would I write a computer code to solve them? Actually, how do you write a computer code to solve some equations? It actually educates you sometimes on what the physics is going on. So we have to understand the physics, we have to understand the mathematical background, and then we have to understand the numerical methods afterwards. Right. So if we just take one part of the left-hand side of the equation, what is that doing? That's telling you that the information, in fact the velocity, is propagating at a speed u. So in a little time step, it will have moved a certain distance. So information, the velocity is moving, and it moves a distance, delta x, which is given by u delta t. You might, in designing your numerical calculation, want to make the spatial grid smaller than u delta t, so information doesn't jump way down the grid. It only moves a little distance each time, and a little distance is measured by the spatial resolution. Or in other words, you might want to reduce the time step so information doesn't go too fast across the grid. There's then, if we take the left-hand side, the first term on the left-hand side and the furthest term on the right-hand side, there is a diffusion equation. So there's a diffusivity of momentum, which is the kinematic viscosity. That's the dynamic viscosity. And the diffusion equation moves in a time delta t. It moves information a distance delta x, which is the square root of delta t. That means that in very small times, it actually goes quite a long way. But in long times, it's sort of relatively slows down. So again, there's this issue. You might want to reduce the time step so it doesn't go further than one grid block. That actually pushes delta t down to very small. So if you're thinking of this, a spatial resolution of, say, 100 points across the grid, you've suddenly asked, typically in non-dimensional times, the time step to be 10 to the minus 4. So information doesn't go. That might not be a clever thing to be wanting. You may want to have a slightly coarser grid so you can have a larger time step. Or you might want to know how to handle that physics a little better. And then one of the really awkward problems is if we look at the acceleration driven by the pressure gradient, the equation there is with the incompressibility condition. What we've done here is really we've got a compressible fluid, but we've set the speed of sound equal to infinity. And so this part of the equations can send information from one side of your experiment to the other side of your experiment in 0 time. We've put the speed of sound equal to infinity. If you push a wall sideways, then the other, and on a tube, if you push the plug, I'm afraid the fluid comes out the other side instantaneously, however long the pipe, if it's incompressible. So this is the first hint that pressure is not a friendly thing for the computing. Okay, so there's a Reynolds number, which I hope you okay on Reynolds number. We'll define it in a minute. There's various things that happen. At low Reynolds numbers, vorticity diffuses very rapidly, and you work in a quasi-static situation. Every instance is in equilibrium. That's difficult for the computer. You have to resolve very fast diffusion of vorticity in a time-dependent calculation. At high Reynolds numbers, there can be thin boundary layers. So you need a high spatial resolution to understand things. So for this simple problem by simple methods, we're going to stick in the middle. And Reynolds number of 10 is the middle. Reynolds number 1 is low. Actually, Reynolds number 10 is quite low. Reynolds number 1 or 200 is high. So in the middle, I'm going to do 10. It's on the low side. But I can't solve it analytically, like 0 Reynolds number. Right, so that's, do you know your physics? Do you know your mathematics? If you've got a set of mathematical equations, what is a sensible question? And a question is not just the equation, but it is the boundary conditions, BC boundary conditions, and the initial conditions. If you have an equation with the wrong boundary conditions, then a solution might not exist. So what is a well-posed problem? You have to supply the right initial conditions and boundary conditions to an equation. So you better understand this mathematics because you're going to do it in a numerical version. So for this first part of the equation, that the left-hand side where we had velocity being propagated with u, that sort of equation is a hyperbolic equation, a first-order hyperbolic equation. It's well posed if you know the function that is being moved around, which I've got here as phi, if you know it everywhere at the initial moment, and if you're working on a boundary, say you start at x equals a and go to x equals b, and the velocity is positive at x equals a, you're going to have to tell me what is coming in, what is inflowing. So you have to tell me the function phi as it comes in over the incoming boundary. It's obvious, but if you didn't tell me that and didn't say anything to the computer about what's coming in, it will invent nonsense. So that's the first order equation. We don't have a second order hyperbolic equation in the in this simple problem we're going to tackle. That equation with 2 time derivative equals 2 space derivatives and a speed of propagation c, that is only well posed, sensible mathematical question if you know the initial data of the function value and you know its initial time derivative, because it's a second order equation in time. And again, at the 2 ends you have to say something. You might want to say the value or its derivative at both ends, because you've got information propagating in at both, from both. This equation propagates information in both directions at a velocity c. Okay, Laplace's equation, we're going to end up spending all our time solving this equation. It is well posed if the Poisson equation with a non-zero right-hand side, if the function, if you tell me its value on the boundary or its normal derivative or some mixture between the two. Is that all? Oh, and the diffusion equation. So we do have a diffusion equation in the Navier-Stokes equation, and this is well posed if we know the initial value of the function that's being diffused and we have to know, because it's second order in space, two space derivatives, we have to know information at both ends, either be told at each end the value or the normal derivative or some mixture of those two. There's some restrictions on that too. Okay, so there are these words, hyperbolic, elliptic, and parabolic, and they come from thinking about this general quadratic equation, and you can that describes a surface in xy, and that surface is either a hyperbola, a parabola, or an ellipse. And if you just translate the coefficients from your partial differential equation up to that and find out what it is, that tells you those funny names, which is not important. Okay, but what is important numerically is that the hyperbolic equations, propagating information along, is very tough numerically. Because if you make a mistake, it will just propagate your mistake. And at the next time step, you make a new mistake, and it will propagate that. And after time one, your solution is swamped by errors that you've picked up. It's a very difficult equation to solve. The elliptic equation, the Poisson equation, is fairly costly. As I said, 95% of computing time is spent solving it in fluid mechanics. The parabolic equation, the diffusion of heat or diffusion of momentum is the safest. You can make mistakes and they just go away by the next time step. It's a beautiful equation to solve numerically. Right. So we're not quite finished about this preliminary thinking about what's going on in our equation we'd like to solve. There is the issue of the velocity that we prescribe along the top. Why don't I want to have a constant velocity on the top? If you have a constant velocity on the top, then near to the corner, the stress, the viscous stresses, the pressure and the viscous stress are inversely proportional to the distance from the corner. And therefore, when you want to integrate the force, the viscous force along the top to find the total force, you're integrating 1 upon x from x equals 0. Doesn't work. True, the computer will give you an answer when you ever ask it a question, but the answer will depend on your spatial resolution. And the more you increase the spatial resolution, the bigger the force gets, because it's trying to be infinity. So you don't do a constant velocity along the top. And in fact, so slightly better would be to say, let's have a linear function, a function that vanishes equally at the two ends, so that sine x vanishes at x equals 0 and pi. Linearly, that unfortunately gives a stress which is logarithmic. It's the pressure that's logarithmic at the ends. And while I can integrate log x from x equals 0, it's not too easy. So it's difficult numerically. It can be persuaded to work, but I'm not going to do that. I'm going for something even safer, because I want to do simple things and show that I get accurate answers. So I'm going to make the velocity vanish quadratically, like x squared at x equals 0 and at x equals pi, x equals L. So when sine x is equal to pi. So I've got a quadratic variation at the two ends. So therefore my stress is order 1 at the ends, and the viscous stress is order 1 all the way along from the two ends, which are potentially singular, but are not now. And so I'm going to get a finite answer for the force. And it won't behave absurdly as I change the spatial resolution. Okay. So that's a sort of, before you solve a problem, you should have a little discussion with yourself about, do you know the physics? Do you know the mathematics? Are there any awkward problems lurking there?